And up first, we have Michael Barker talking about Moonba.
Hello?
Yep, we can hear you.
Okay, great. Okay, so thanks for giving me the opportunity to speak today and introduce a concept for a micro-rover or a targeted investigation of lunar regolith. And my collaborators at Goddard are Tim Livengood, Dina Bauer, and Tilak Hewagama. Next slide. So as we've heard today, the surface of the moon is covered in regolith, loose, unconsolidated soil with typical grain size of several tens of microns, and it's the source of much of what we know about the moon. Yet we've never really directly observed it at the grain scale in its natural state. Remote sensing studies of the moon and other airless bodies throughout the solar system often invoke microstructural changes to the regolith related to its porosity, surface roughness, and these elaborate grain structures called fairy castles to explain remote sensing data over a range of wavelengths. But these hypotheses have never been directly tested on the moon or any body. Next slide. Unfortunately, return samples and photos from the moon are largely inadequate for definitively testing such hypotheses. The Apollo and Luna regolith samples have revolutionized our view of the moon, but their compaction states in the top few microns were likely fundamentally altered by the collection, transport, and storage in Earth's gravity. The highest resolution Apollo photographs, such as the background image here, were taken with the Apollo lunar surface close-up camera, shown here on the right. These images are really best for studying surface roughness on scales larger than about 1/10 of a millimeter in the vicinity of the landers where the natural grain surface microstructure was likely disturbed. Next slide. In 1963, Hopke and Van Horn hypothesized that the moon's top surface layer is extremely porous with many interconnected cavities. They conducted lab measurements of the optical scattering properties of many different surfaces with the goal of understanding the moon's peculiar photometric behavior, namely its low albedo, the sharp ubiquitous brightness enhancement near full moon, and the relatively little limb darkening observed across the face of the moon at full moon. And so they noted that if a dielectric, such as a piece of rock, is pulverized and sifted to small particles, which are then deposited individually in the lab with low velocity, the grains can build up these complicated structures of towers and branches that they called fairy castles, such as in this photomicrograph of a sieved cement powder magnified by 53 times. And they saw that grains in these fairy castles can be supported by only one or two adjacent grains through adhesive forces. And they thought that the fairy castle microstructure could be built up over geologic time by electrostatic transport or micrometeorite bombardment. And Hopke and Van Horn found that dark surfaces with such porous microstructures, much larger than the wavelength of light, can backscatter light towards the sun as strongly as the moon. And so they concluded that the top surface layer of the moon must have a very high porosity, perhaps as high as 90% or so, with many interconnected cavities. Next slide. And so since that time, it's often hypothesized in the literature that changes to this top layer structure, if it exists, may be contributing to many of the variations in reflectance behavior seen in remote sensing data for the moon and other bodies. So from lander blast zones to new craters, swirls, and permanently shadowed regions, also to fresh crater ejecta on Vesta, the changes in reflectance properties at these sites suggest changes to the fairy castle structure, although there are competing explanations, such as changes to the surface roughness on slightly larger scales, like millimeters to centimeters, or the redistribution of materials. So there may be competing processes operating on different size scales, and it's not really clear yet which, if any, is dominant. And since we're targeting the South Pole for human exploration, I just want to highlight here the uncertainty that still exists in the role of enhanced ferrocastling and porosity in contributing to the darkening of PSRs in the far UV as observed by the LRO lamp instrument. It seems likely that some amount of ice is required to explain the far UV spectrum and other measurements, but the exact amount depends to some extent on the porosity assumed for these regions. And it's been hypothesized that reduced thermal cycling or dielectric breakdown could potentially enhance the porosity in the PSRs. So this has important implications for how much ice is inferred from various measurements. So direct in situ measurements of the regolith porosity in PSRs would help address this issue. So these are just a few examples of how the surface microstructure may be contributing to reflectance behavior variations on the moon and other bodies. And what we need is direct in situ validation of this hypothesized structure for untouched regolith for any airless body at relevant resolution, as well as sampling the diversity of the surface over transect comparable to orbital pixel scales. Next slide. So our concept for a solution is Moonba, a micro-rover for a targeted investigation of lunar regolith, maybe more appropriately dust. The goal is to understand the top layer structure and its effects on remote sensing measurements through the systematic and coordinated 3D microscopy and photometry of regolith in its natural state with a small rover microscope and lighting system. And so this is critical to the correct interpretation of surface observations from remote sensing and in situ studies of the moon and other airless bodies. So Moonba and a PSR, for example, would address multiple decadal survey questions related to the distribution, sources, and sinks of lunar volatiles. And regardless of site location, these types of measurements can provide much needed initial condition constraints to models of dust transport processes. Next slide. So Moonba would be implemented as a small wheeled rover carrying no batteries, minimal power distribution, no data processing system, and no wireless communication, operated on a lightweight tether from a fixed base station that supports communication with Earth. And offloading power, control, and communication to the base station enables a low-mass rover. The base station could be deployed by an astronaut, or it could be on the lander itself. The tether would provide two-way fiber optic data transmission and power delivery that carries current to warm it and keep it flexible in shadow. And the tether can deploy from motorized reels on the base station and on the rover to minimize drag. And it could enable the rover to venture into PSRs at tens of Kelvin and increase power to heaters to maintain operating temperature. Next slide. So primary instrumentation would be a down-looking monochrome 3D microscope with roughly 10 micron 3D resolution, meaning capable of resolving structures about 10 microns in size. Also a ring lighting system to control illumination angle, including direct co-aligned lighting with commandable color distribution. And additional instrumentation would include moderate resolution 1 to 2 megapixel cameras, forward-looking and reverse, and on the base station, all for context and remote driving control. So Moonba would move very slowly and methodically, minimizing grain scattering or ground vibrations that could disturb fragile grain structures. And the primary driving goal would be to drive nearly straight away from the base station to characterize the soil structure at multiple distances, and this is key, reaching beyond the blast zone for a systematic sampling of regolith structure and diversity. And the high data volume that would likely result would probably require that only a selected fraction of data be telemetered to Earth. But with astronaut deployment, the full data set could be stored on a device retrieved by astronauts and returned to Earth. And next slide. So to wrap up, if I had to summarize the sort of motivation into two top questions, it'd be, what is the 3D microstructure of undisturbed regolith, and does this structure change in permanently shadowed regions? And so our concept for addressing these and similar questions is for a small rover to do with lunar regolith and dust and its 3D microstructure and the effects on remote sensing data. And these measurements we think are very important of any. They cannot be made in the lab on Earth. And they address a diverse set of goals with cross-cutting application to the areas of human health and safety. So with that, I'll be happy to take any questions.
Okay, thanks, Michael. I think we'll save the questions for the discussion section because we are a little bit behind on time.